Okay, hello everyone. Welcome to today's Oticon seminar. Thanks very much for coming on, and thanks again for Oticon for giving us the funding to put on these seminars. Today we've got two talks by Kai Luz. The first talk is by a PhD student of ours who's about finishing his PhD, and Andy King, and he's going to be talking about the effects of age and hearing loss on auditory processing.
Right. So we're going to be looking at specifically neural synchrony and interaural phase difference discrimination. So I'll start by explaining what I mean by neural synchrony. I basically mean phase locking, and that still doesn't make any sense, then hopefully this figure top might help. So when the vascular membrane moves in one direction, the nerves that are attached to it will fire, but they won't fire when it moves back in the other direction of its oscillation. And this allows the nerve to lock to the phase of the cycles of the stimulus. By doing so, this allows you to have access to the interaural phase differences. And the interaural phase differences are basically the minute differences in time that occur when a sound from, for example, from your left is to your left and for your right. You're going to have an interaural phase difference because that's that very small time difference. And because these nerves are firing only at a specific point, that difference in time, or the other phase of the sound, is retained in that encoded signal. And this is a way you can determine where about you sounds are coming from, whether they're coming from your left or from your right. And it's probably going to be quite useful for localizing sounds, and also for separating out sounds in a noisy environment. So if someone's talking off to your left and you want to ignore them, and you want to listen to someone talking to your right, then your brain usually use these interaural phase differences in the two sounds to suppress listening to this one and focus on the right instead. As we get older, there seems to be some evidence that we are less capable of sensitive to these interaural phase differences, and this might also be related to our to age-related changes in hearing speech in noisy backgrounds. So the link between poor ability to use these IPDs and actually listening to one speech and ignoring something else from a different angle. So that's what we're kind of testing here is the degradation of the ability to use these interaural phase differences. Is that kind of explained by changes in the neural synchrony, the underlying kind of phase locking in the auditory nerve? So the first questions were, do age and hearing loss affect IPD sensitivity independently? And second of all, do age and hearing loss affect neural synchrony independently? And then finally, if neural synchrony explains IPD sensitivity, does that explain the age-related effects on IPD sensitivity? Fortunately, I'm not going to cover hearing loss in this talk, partly due to the data we collected, and I don't have time either. So I'm just going to focus on the effect of age. The way that we tested people's sensitivity to interaural phase differences is using these tones you see on the screen. So these pulse tones in panel A have an interaural phase difference in the kind of the carrier, or the amplifying structure. So you can see that the blue one peaks just before the red one at the top peaks here. But they both have the same kind of overall fluctuation, or the envelope of the sound is the same, but the amplifying structure has an interaural phase difference in it. Whereas in panel B, you can see that they both have the same peaks at the same time, or you can say that they cross zero at the same points. So there's no difference there. But you can see that the envelope fluctuations are later in the red signal than they are in the blue. So if the blue was your left ear and your red was your right, say you've got a interval phase difference in the envelope but not in the fine structure. So you can independently test people's sensitivity to IPDs in the TFS in the envelope as well. So the actual listeners that we tested IPD sensitivity with are plotted here in terms of their age and their hearing loss. So in the left panel, this is their absolute threshold at the low frequencies at which we tested their IPD thresholds. And in the right panel is their high frequency audiometric thresholds, and you can see that they're quite related to their age. So as you get older, your high frequency thresholds are worse, and this is quite common. So in this talk, you have to bear in mind that the effects of age that I'm talking about may be related to their the high frequency thresholds of our listeners. You can see in the low frequency, there's not a lot of hearing loss above 30 dBSPL. So, to say one of the reasons why we've not discussed hearing loss too much, we don't have enough data from people with substantially elevated thresholds to test this effect. So these are the people's thresholds of the smallest IPD they can discriminate, plotted by their age. And for the envelope IPDs, you can see this relatively good progression. As you get older, your threshold gets higher, larger. So that means that they're getting progressively less sensitive to envelope IPDs as they get older. And something similar is seen in the temporal fine structure, which is a bit more scattered. Again, it's basically age seems to give you a greater ability to determine interval phase differences, which is consistent with the previous research. We wanted to see whether this is being driven by the neural synchrony. So we used a frequency following response, which is an EEG measure, and you're looking at the essentially how well it follows the periodicity in the signal. So if you play a tone to them, what you get out with your FFR is basically approximating a tone, and this happens because of the phase locking in the brainstem as well. And everything else that's not a response to that sound should get cancelled out over a great many average EEG trials. So we played some more modulated tones, a little bit like before, but we played different ones to each ear. So the left ear had a slow modulation up here, and a faster modulation here, but they're slightly different modulation rates to what the right ear has, and they're carried, switched over the carriers from the fast and the slower carriers, which one carried the higher and the lower modulation. And we recorded our FFR with two electrodes, montages, so we recorded it from the forehead to the back of the neck, it was vertical, and we recorded from one mastoid to the other, and that was our horizontal. And this might give us slightly different sensitivity to different parts of the FFR. But I won't really go into too much detail on that today either. So we're just going to look really vertical mostly. The other thing we did is we essentially played the modulated tones in two different polarities. So you start with one where the waveform kind of starts going up to start with, and then you if you flip that waveform upside down and then play that afterwards, potentially got an inverted version of it. And then if you add together the responses to these two alternating polarities, you get the black bit here, which is the envelope, that gets increased in the response. And if you subtract the two responses, you get the grey, which is the kind of fine structure, that should get increased, and the envelope should get the response to the envelope should be diminished slightly. So these are spectra. So that's the frequency is plotted along the x-axis, and what I'm plotting on the y-axis is phase coherence. So that's how at each frequency, how across all the trials, how well the phase kind of matches up. So if the nerves are firing really precisely the same phase to the signal each time, then you should get really high coherence. If they're kind of firing it more randomly, you get a low coherence. And I've plotted them here red and blue for the younger and older subjects, and you can see that the younger subjects have higher peaks at where these little arrows are, which is where the test tone frequencies were. So on the right hand side you've got the subtraction response, the response to the actual the defined structure, and in the left you've got the response to the envelope. You see, for most of the envelope they're kind of not hugely different, but there is at this peak here, you see the difference. So there is a large age difference here too. If you do look at the differences between people with elevated thresholds, low frequency, there's a slight difference up here, but it's not very great. As I say, we decided not to look at this with the sample of people we had. So if you kind of take for each listener, you take their kind of average phase coherence at this point and this point together, and at this point and this point here together, and you plot that across the listeners for their age again. So low mod rates is this green and yellow one, and the high mod rates is the blue and pink one here. You can see that there's slightly different relationships, but the lower modulation rates is not very strong correlation, slightly positive. Higher rates, there's a negative correlation, which suggests that as people get older, they're less able to, the neurons aren't synchronizing to the modulation as well as they are for young people. And if you look at the fine structures, this is from the subtraction, you can see that for this right hand panel here shows this bunch up here. You can see that there's says the red's the young and the blues old. You can see as we get older, again there's a reduction in the synchronicity to the stimuli. There's also similar correlation found for these ones down here, but it's a bit more suppressed, so we're going to focus on these ones for testing whether this is related to their IPD thresholds. So this is comparing their phase coherence, the neural synchronicity, to their interval phase differences, and you can see that there's not much of a correlation, slightly negative, but these aren't significant. So essentially, it's not. Although both are deteriorating with age, the relationship between the two is not strong. And if you partial out the effect of age, so that's this you've just seen this panel here, you lose any semblance of a correlation. Whereas if you look at their IPD thresholds against their age, like we did at the very start, that's the first set of results. You can see that if you partial out the effect of neural synchrony, there's still a relatively moderate correlation, at least for the envelope. So some other age-related factor is affecting IPD thresholds that's not necessarily predicted by phase coherence or the neural synchrony, at least the envelope, and possibly to some extent the defined structure too. So that's pretty much what I've just said in conclusion. So the implication though that there is some of a link between phase locking and aging, but this might not necessarily be the same. There's a link between interval phase difference discrimination and aging. So maybe interval phase discrimination and age, and how that relates to locating sounds in different directions, is modulated by some high level processing in the brain that doesn't show up well from a kind of neural, the very kind of low level neural synchronicity. That makes some sense. Stop there.
So I have just a couple of questions. Mike had one.
Why are you calling it the FFR? I mean, Chris had scribbling over something I wrote recently because it's not down that you're following the envelope modulation response, so level 1 ASSR. Or what's the terminology?
Between FFR and ASSR? Well, I'm not sure that the ASSR is used to find thresholds, so it's you would change the level until you don't get a response. They're not necessarily so interested in the actual synchronicity itself, but synchronicity is inherent in the response, right? So you need to have synchronous responses to get a larger response that will give you a threshold. So for the modulation effort, the envelope FFR, I'm not sure exactly what the difference is between that and ASSR, other than the no. I was going to say other than the carrier frequencies, but because I use quite low carrier frequencies, ASSRs typically come with higher carrier frequencies, I think.
I have a question I'm going to ask. What do you think explains the poor control phase differentiation in old people if it's not fidelity of understanding? What is it that changes with age that's important?
Well, that's the thing. It's from my work, you can't really tell, but there's a lot of other work that's shown kind of deficits in certain cognitive measures, particularly selective attention. So if you've got a talker to your right, not your left, then you have to listen. You have to kind of attend selectively. So that makes sense that if that deteriorates with age, then that's going to also affect your ability to separate out sounds. Whether that's actually related to IPDs or not, I'm not sure. It's certainly related to the bigger picture, more like what we're doing in the actual environment. But yeah.
Did you want to ask you a question, Chris?
No, I just saw it.
Right. Okay. All right. Thanks very much, Andy.